Okay, I think we'll start back up. Did everybody get enough to eat for lunch? If you didn't, there's cookies in the back. There's more than what's there. If you don't eat them, I gotta take them home. And dinner will be at 6, and there's a massive taco bar. So if you didn't get enough to eat, you should be okay come the end of the day. The other thing I should warn you about is I've given Conrad another device that is a remote for each chair, which has an electroshock in it. So if he notices anybody dozing, he can hit that. No, I'm just kidding.
Well, the laser should wake him up.
That'll do it. As I introduce Conrad, I'll say that you probably noticed in the rules for JSHS and many others, you see that there are no, you can't bring anything, any devices to show or any show and tell, and there's a reason for that. Conrad's a reason. I say that in all good ways, as you'll see. It's my pleasure to introduce Conrad Farnsworth from Newcastle. Conrad.
Hi, my name is Conrad Farnsworth, and of course I'm from Newcastle. This is my project called Shooting Higgs Bison. It's a quest for a more efficient nuclear fusion reactor. This device behind me is a culmination of 4 years worth of research development, blood, sweat, tears, and lost sleep. It's actually the first of its kind. It's actually never been implemented before inside of a nuclear reactor. Now, what is all this? So let's move on. Oh, what am I doing? Okay, let's move on. There's 2 types of fusion that can occur within a nuclear fusion reactor. The first one is that 2 deuterium nuclei collide, and a neutron comes off at 2.45 mega electron volts, so 2.45 million volts. Now, how these nuclei collide is from the inertial electrostatic forces. So we have what's called an inner grid right here in the center. It's a 4-way stainless steel cross, electrically suspended from a high voltage insulator, and it's not touching anything within the stainless steel chamber, of course. And it's held at a high potential. And what this high potential does is it accelerates and ionizes these deuterium atoms. And when they collide, if they collide, they might fuse. And it's all a game of probability from then on. So moving on to the second reaction we have here, we have 2 colliding again, and a proton coming off at 3.02 MeV, mega electron volts. I can't actually detect this proton because it requires a CR39 detector, which I don't have access to. So moving on further, there's 5 separate systems: the vacuum, the chamber, the electrical, the gas handling, and the radiation monitoring. I'll go into these separately. The vacuum here, the reason we need to draw a vacuum during fusion is because you can't have fusion when you have particles in the way. It's like trying to tackle somebody in a swimming pool. It can't happen because you're just going too slow. So we draw this deep vacuum, as deep as we can, and so deep that it actually requires 2 pumps. Moving on further, we have the chamber, which is what the Einzelenstractorgun, the star of the experiment, is mounted on. The chamber is where all the magic happens. It's 6-way cross, various flanges, gate valves, vacuum control, and as you can see mounted right here is the boron tin tube that is used to detect the neutrons. And up above here is the electrical assembly, which I'll get into next. All of this holds the inner grid, as I'll refer to it, which accelerates, ionizes, and actually does the brute force, the brute work of this project. So moving on to the electrical system here, I have 30,000 volt power supply and an ion gun power supply I made out of microwave ovens, some electrical tape, a light bulb, and alligator clips, and a high voltage diode I found. It multiplies the voltage 10 to 1, so you'll see voltages in my experiment that say 55 volts. That's the input voltage, and you'll see 550 volts. That's the output voltage. So they're one and the same, it's just input and output. And then moving on, here's my gas handling system. Radiation monitoring, how this works is you have the neutron that comes out that's actually coming out too fast. And what it will do if it comes in too fast is it'll hit the boron tin inside the tube and actually obliterate it. It'll just destroy the atom and you won't get a usable signal for detection. So you have to run it through this moderator. And what it does is it bounces around off of hydrogen atoms inside the paraffin, which is heavy in hydrocarbons. And it deposits the kinetic energy within the hydrogen atoms and slows down to about half a mega electron volt to 1 mega electron volt, where it embeds into the boron tin tube, turns it to boron 11. The boron 11 decays into a lithium 7 and an alpha particle, and the alpha particles actually produces a very unique signal that this Ludlam Model 12 detects. And then this is the primary measurement of the primary measurement device of the experiment. So this is critical that we are able to measure neutrons coming out. And so one event occurring is one event occurring in a minute, 1 count per minute, 60 in a minute, etc., etc. So I use rate to calculate efficiency. Moving on further, here's the Einzelenstractorgun, as I have previously mentioned. It's composed of a 2.75-inch conflat vacuum flange, which I have machined and fitted various ceramic insulators and stainless steel electrodes. As you can see at the front of the gun, we have 2 plates at 0 volts and a center plate at negative 60 volts, and I'll get into this later. Moving back, we have the ion gun segment. The flange, this is where it ends the vacuum, and here's regular atmospheric pressure. Then we have the ion gun connection for the high voltage, and then we have a non-conductive tube to the deuterium gas supply. Moving on, here's another view. Continuing, here is the frontal view I originally manufactured for, but due to various inconsistencies within the parts that I ordered off of McMaster Car, I was actually unable to make 4. I had to cut it down to 2, which then had to be cut down to 1 because I was having trouble holding a vacuum with JV Weld. Now, this is just a picture of the frontal, the business end, I guess, of the ion gun. The Einzelens is not attached here. As you can see, we have an outer ground sheath, which is electrically connected to the flange, which is connected to ground. A ceramic insulator to isolate the stainless steel tubing, which is held at 550 volts to 1,360 volts. And what happens here is the gas comes out of this, and it's at a high enough pressure to where it allows conductivity within this ion gun portion. And what that conductivity does is it actually ionizes the gas within and creates fusion-ready ions. And you can't have fusion without ions because the electron shells will actually repel. So more ions, more problems. This is the assembly mounted, of course, onto the reactor with a vacuum release valve attached. So let's go into how all this works. Gas comes in through this plastic tubing right here, which is electrically insulated, very important. Goes into the stainless steel swage lock mounting barrel. Goes into the 1/4-inch tubing. It goes into the ion gun, where it's at a potential 1,360 to 550 volts, is ionized, is drawn through the ion gun assembly through the Einzelens, which I'll get into here, towards the inner grid. So this is actually pointing right at the inner grid, which is somewhere around here. Now, what it does is this is images reversed, of course, is it pulls the ions through, and the electrostatic forces within the Einzelens actually shape the plasma and change the focal point. Well, why do we want to change the focal point of this plasma? Well, the thing is, you can't have fusion at high pressures because the density is too high. But if you can increase the density at the point where the velocity is the greatest, i.e. the center of the inner grid, then you can increase your chances for fusion, i.e. increasing efficiency. So with this, I formed 2 hypotheses. One was if the Einzelenstractorgun's ion assembly is on, then the counts per minute will be significantly higher than the control. And the second one was if the Einzelenstractor's ion gun portion assembly is activated and the Einzelens is at a potential 60 volts, then the neutron output rates are going to be even higher than hypothesis 1. So moving on, here's my experimental design. I did 5 trials with my control. The inner grid is on this throughout these entire time because, as I said earlier, it's kind of like the workhorse. It does the fusing. So the inner grid's on at 30 kilovolts. Then I tested the ion gun at these 3 input voltages, 5 trials each. Then I had the control, ion gun, and Einzelens on, and I tested the 3 potentials again with the ion gun. And here's the control portion of my 5 runs. I got about an average of 360 counts per minute. Moving on, here's my raw data. Moving on again, here's the data between the ion gun and the ion gun with the lens at the various output voltages, of course. Moving on, we're going to get down to brass tacks here. This is the average counts per minute for the control, 336 counts per minute. When I turned on the ion gun, I raised the counts per minute by 300-something counts per minute and got 668. When I turned on the lens, actually, I experienced an actual decrease in counts per minute. Then I decided to run my one-way ANOVA, and I found that I was statistically significant between the ion gun and the control. I had a p-value of 0.003, which is much below my threshold of 0.05. Then when I ran my one-way ANOVA between the ion gun and the Einzelens, I had a p-value of 0.1, which is above my threshold of 0.05. And then here again is the averages of the 5 runs over input voltages with and without the lens. So let's get down to this. What happened? Hypothesis 1 was supported. I had a 126% increase in efficiency from the control. So just by turning on this ion gun, I was able to increase the efficiency of a nuclear reactor by 126%. However, hypothesis 2 was not supported. When I turned on the ion gun, the Einzelens, I actually experienced an 11% decrease from the ion gun. However, this is still an 85% increase from the control. So from just having the reactor on. So why was this? First off, the Einzelens actually has a lot to do with surface area parallel to the beam path. What you saw was a lot of surface area, but it was actually perpendicular to the beam path. So that could have skewed my results. And secondly was the plate calibration method. I actually had to raise the pressure, the internal pressure of the reactor, not, of course, above atmospheric, but I had to raise the pressure of the vacuum and actually calibrated at a much higher pressure, which also could have affected my results. So the applications. We have the good. It's flick of a switch control with radiation. We have possible for medical imaging, also known as PET scans, PET, positron emission tomography. And you can irradiate isotopes within a person's body using a reactor like this. And then when you shut off the reactor, the isotopes will decay, but you're not going to have excess isotopes sitting around decaying. You also have cancer treatment, on-site isotope production, so you aren't actually shipping these dangerous medical isotopes to hospitals and then having all sorts of extra exposure that you don't need. Also, what's called active interrogation with Homeland Security. Homeland Security uses active interrogation, and what you do is you bombard an entire room with neutrons. And the neutrons irradiate everything, and then you get this like reflection back. And this reflection has each element reflects differently. So it's kind of like spectroscopy. You have very specific peaks within a room. So you're actually able to detect nuclear devices with just by simply irradiating your room. The next, you basically have unlimited power. You don't have to worry about being tethered. So just think like Iron Man. You're gonna have technology that doesn't require tethered power, which is like this opens up this whole new realm of things like Robert Downey Jr. flying in an ion-powered suit because all of a sudden you don't have tethered power. So moving on, we have bad. It's actually very hard to shield neutron radiation. So that's also an engineering feat that needs to be accomplished. It's also the second most dangerous type of radiation, second to alpha only. We're not at optimal neutron flux yet. If I were at optimal neutron flux, I wouldn't be sitting here talking to you, I'd be a pile of dust. It's also not, we don't have an efficient capture technology. We have what's called, what you do is you irradiate a lithium bath, and then you have losses in the system just by simply irradiating the lithium, running it through turbines, and it's a very lossy system. So we don't really have an efficient capture technology quite yet. And we have the ugly. You could basically use this thing for uranium enrichment if you ran it long enough and at high enough levels. It's also, you could use it technically for non-structure compromising target elimination, so you could spare the building but get rid of everybody inside. And should Robert Downey Jr.'s suit leak and radiation get inside of the suit, then really you wouldn't be able to stop much. It's actually quite deadly, other than the fact that you could actually flip the switch and turn it off. You wouldn't have something like Chernobyl, which is an incredibly great positive to a nuclear fusion reactor. Here's my bibliography and my acknowledgements. Thank you.
So Conrad, you mentioned that you can't measure proton release. Do you feel like that happens at the same rate as the neutron release, or do you know if that happens at the same rate? And do you feel like with the ion gun or the lens that you would get more protons or neutrons one way or the other that you might be missing out on?
Yes and no. Okay, so as I said earlier, it's a 50-50% chance of reaction occurring. So really, just take those numbers and double it if you'd like the total isotropic emission rate, as it's called. When you have 3 million volts against 60 volts, it's really not going to do a thing to, say, the proton. The neutron, it's not going to do anything to. However, so you're not really going to have to worry about neutron radiation. Proton, it's really not going to do anything to either because it's at such a high energy level.
So I was just trying to wrap my head around that. So typically when you're trying to do a fusion reaction, you have your containment field, and then you shine a laser into it to get up to the correct amount of energy. But instead you're using beams of, are you using beams of electrons to basically bombard the deuterium, or are you bombarding deuterium into the reactor?
Well, what's happening is you described inertial confinement fusion, which uses lasers. Right. And it actually uses a lot more power. But this is inertial electrostatic confinement fusion. So what it does is, since the protons are positively charged and not at such a high energy level, when they're ionized, they're actually attracted. They're no longer electrically neutral, so they're attracted to this inner grid. And what this inner grid does is it lenses. It lenses the ion field. So you can kind of see, this is kind of during calibration, of course, at a higher pressure, but you can kind of see the exaggeration on how it actually accelerates and lenses and influences these deuterium atoms. And what happens is you kind of have this circulation going on inside the reactor. And hopefully you'll have a circulation to the point where there's two actually coming in from opposite sides and then colliding and then fusing. Then it's all a game of probability, of course. Actually, most fusion within a reactor isn't done traditionally. It's done through what's called quantum tunneling. It's all probability. You can't have high enough energies within an amateur reactor to actually brute force fuse.
Okay, that's what I was kind of. I wasn't sure if you, because you need like 10 to the 5th Kelvin for this kind of stuff. So it's just,
It's 600 million degrees Fahrenheit. So it's at fusion temperatures. Yes.
okay.
So you had in your measuring your what was it, paraffin block, right?
Yes.
And then your boron 10 tube.
Mm-hmm.
What's flowing into the paraffin? Like, so I guess what I'm asking is there a set direction that the neutrons are coming out?
The
of
neutron,
your apparatus?
the neutron emission is actually isotropic, so it really doesn't matter where you put the detection block. It's just that it really doesn't matter where you put your detection block because they're coming out in all directions. It doesn't really matter when you fire two cannonballs at each other. When they explode, they're really going to go whichever way they want. So having this block right here, it really doesn't matter, but how you place your paraffin is important. So this actually, I had a bit of an extra moderator right here, a bottle of water when I did my experiment. And you want, because your origination is going to be at the center of the reactor. So line of sight, you're going to want as much moderation as you can because they are coming out at 2.45 million volts, which is a fancy way to say a lot of kinetic energy.
So if you had more than one monitoring apparatus, I mean, would that be possible? Do you think you'd get more accurate data then?
That would be great because I would be able to get more accurate data. I'd be able to get what's called the actual total isotropic emission rate. Various places like CERN and National Superconducting Cyclotron Laboratory, they have things like that, but these tubes run about $300 a piece, so that took quite a bit of time to acquire one. However, you could actually probably model where most radiation is coming out of, but since it's isotropic, it's almost like not really worth it to spend all this money on these tubes and get kind of a very fuzzy idea, as you can see by the size of the tube, get a very fuzzy idea of where all of this radiation is coming from.
So what's next? What are your plans now?
I'm looking at actually more professional machining. I did this all in my garage. And the funny thing is I was experiencing troubles earlier with leaking, and what I had to do was I actually had to build a clean room, and my dad didn't really appreciate this very much, because he had a car lift, and I actually lifted up the car lift and had a bunch of painter's tape hanging off of it for about 3 weeks, and he wasn't really too happy about that. And so I had to manufacture a clean room to assemble all these parts in, because just a little speck of dust will ruin vacuum seal. So what's next really is more guns. I originally was going to mount two opposite of each other, but I was having trouble with the JB Weld actually holding the vacuum. So of course, I'd probably, if I had the money for it, I would probably go with a more professionally machined apparatus. And actually a better designed Einzel lens, actually, with more surface area parallel.
So you got lower rates as you put in the lens. You think that the more you focus it, the better it would be. Do you think it was some sort of problem with the lens itself, or maybe you're not exactly sure where it was focusing, or what do you think was?
So what probably happened was I was experiencing a bit of sputtering. So like the surface area perpendicular to the path was actually influencing and just kind of spraying it everywhere. So I was still getting out massive numbers of ions, but they weren't in a direction. They weren't actually just being pulled through. They were actually being influenced negatively from this bad plate charge. And that, of course, could have been from the surface area perpendicular or the method that I used to calibrate the voltage that the focal point was going to be at.
So what do you do to improve that?
To improve that, I would definitely do more mathematics. I would probably invest in a software that can model the ion paths. They have very professional software out there, but of course, there's no market for it, so there's incredibly high prices. So I'd probably end up modeling that and actually redesigning just the Einzelens portion. I mean, the ion gun portion works just great.
I don't think this is probably a problem, but what about other electric fields around with that? Maybe cause some of that sputtering?
No, because seeing as the entire chamber acts, it's like a giant Faraday cage, so any actual radiation, electromagnetic radiation, is going to hit the chamber and go straight to ground.
Okay.
There's other than the viewport right here, which some radiation could get in. They actually use, unless I had like a microwave oven, like magnetron sitting there, which fry my brain. But, yeah, that was like really the only type of radiation that really influences deuterium, because it's resonant at that 2.4 gigahertz, which is what the magnetrons are at.